No, no, está bien.
Yo creo que
Ah, vale, bueno.
yo creo que con
Sí,
eso.
con eso. Hombre, ¿qué tal? ¿Cómo estás? Bien, bien. Exacto, exacto, exacto. Claro, claro. Exactamente. Sí, vamos.
Ah, es verdad. Pues escuché algo.
Cuando pregunto. Sí, sí,
¿Hay alguna pregunta? Lo grabamos y eso. Lo dejamos. Espera.
pero... Ah, sí.
Ahora bien,
Sí, sí, es complicado. Y suegra en principio también. Vale, sí. Claro.
La mayoría de la gente. ¿Quieres?
Ya no sé.
Claro. Claro. Oh, sí. Ya, igual es porque fue largo. Hello, everybody. Welcome to this keynote day of workshop. We have here and prepared his in functional analysis. And he has started the University of Juan Carlos de Max where he's working on now at New. And today he's going to talk about special networks using machine learning.
Okay. Okay, so the of the lecture, you know, if you're familiar tensor networks. So the idea of today is to briefly introduce tensor networks, but with a very particular goal in mind, which is their use in machine learning. Tensor networks, mathematical answers, successful, and quantum matter, simulated, how long, but also to understand. But here, I mean, the idea is to show that this technology, mathematical technology that merges the section between quantum information and quantum matter, can have also some use. Oh, please interrupt me. So this is mainly based on these two papers. Okay. So let's start maybe with basics about machine learning. Okay, machine learning is a very broad thing, so basic stuff. So in particular, let's assume that we have a goal, which is to learn a function. Okay. And the way to do that is by searching some suitable variational family. Some neural network and some neurons, some linear or affine function to some nonlinear function that are concatenated through some network. And then, okay, perform all the coefficients coming from the coefficients of each one of the neurons, and then these operations through these arrows get a function, some inputs to the final output. And then the idea is to design a way in which we optimize those parameters so that they close enough to the function we want. Yeah. And for that, we minimize some loss function. That's how close we are to the function we want to learn. And usually, of course, this loss function depends on some data that we have. Learning from data. This loss function usually minimize the error on some training set. But the idea is very simple. It's just minimize some loss function over some variational family, which in this case is given by some parameters and together and the choice of a nonlinear. So in quantum many-body problems, we have very similar things, so essentially. But the goal is to obtain the ground state of a Hamiltonian. And how we do that is, okay, one possibility to do that is to search on some variational family, which is well suited to the problem. Such a family is tensor networks, and I will find them later. But why we choose that is because, I mean, it's known, so we comment that this family approximate well precisely the goal, ground states of local Hamiltonians, and therefore we are sure that we are searching the right family. And so search, okay, we try to minimize some loss function, which usually is energy. We're interested in obtaining data. Okay. And same thing, we have some function we want to minimize, some loss function, energy, that we do on some variational family that is well suited to our problem. Essentially, from this perspective, the things are exactly the same. Okay, so then it's not a surprise maybe that these two areas have been kind of related to each other recently in both directions, but mainly in the direction of using machine learning techniques to solve quantum many-body problems. Something that's pretty fashionable nowadays. Not doing that. Producing families based on neural networks as new families to obtain ground state space. So there's many papers here. Pioneers of that was Roger Merkel, PI, Church. Okay, so but what about the reverse implication? So this is somehow using the power of machine learning into quant math. But maybe for some physics ideas, so ideas coming from many years in to solve quant math problems, could be applied to machine learning. There have been also some results, some papers in that direction. Started with a couple of papers, one of them by Miles Stoudemire, David Schwab, and a parallel paper by Manos Celerets and authors. This idea was introduced there. some papers showing that in some particular setups, maybe tensor networks can behave better than neural networks. One such paper for anomaly detection by this paper. I mean, however, as I said, in very rare cases, tensor networks, physics is fine machine learning. I mean, it's not better than neural networks in prediction accuracy. It's hard to beat. Okay, so they cannot be better. Accuracy can be useful for. Okay, that's some things that we think tensor networks could add. So one thing is interpretability. So one of the main problems of machine learning is that okay, they accurate result, but not either. And some of this can be very problematic for the use of machine learning in context. Can give you very nice answers, very low energies, but you have no clue the physics or anything. Some answer that will low energy, the physics of the system, in a topological order, poker face, can you learn these things? All these things can be learned from the whole series of knowledge in that direction. So tensor networks are very interpretable. Something one can. Okay, efficiency. This is essentially the main area in which tensor networks have tried to enter into machine learning as a way to compress the networks layer by layer by reducing the number of parameters. And also privacy. And that's the goal of this lecture, is to focus on privacy. And okay, interestingly, these three things like interpretability, efficiency, and privacy have been identified as 3 out of 7 key ingredients that should have or should ask for an ethically sound artificial. Big thing now, trying to see the future of artificial intelligence and how it will affect our society, regulate that, figure out this type of artificial intelligence we want in the future, like properties, and these 3. Addressing things. Okay? Okay, so let's start first with the problem. Privacy problem. Okay, so let's imagine something true sometimes that machines are trained in sensitive data. They are trying to find causes of death risk or higher death risk due to COVID. Less fashionable now, but okay, so we have thousands of hospital medical data, and we try to train machines to predict so that we optimize of scarce resources you have in the hospitals. Okay, so fine, but of course, machines need to learn. The output function must have some information on the training data. That's something unavoidable. It's definitely desirable that only the relevant information from the training data is kept in the output function, so that by having access to the machine, you do not learn private data from patients in hospitals that you should not learn. Only the information which is somehow relevant, which is to pay somehow, can be learned. Okay, how can we formalize that? Relevant, which is not relevant. Okay. Before, let's try to find out. Okay, just a very stupid example to illustrate it. Yeah, going to that. So let's imagine that we have to see that tries to separate dogs from cats. Cats in the plane on some curve that separates dogs on one side, cats on the other side. Okay, and then we train our machines into training sets, and the first training set we get this function as a separating function. And in the other set, we get set T1, training set 1, and in the other set, training set 2, we get this other function. Okay? I'm not sleepy to the morning, you realize immediately that they are the same function. You expand y minus 5 squared minus 10 is exactly the same. It's wrong. So it's exactly the same function. But it's described different depending on the training set. Therefore, this is a potential leak of information. So, of course, the way I describe the function is totally irrelevant. The same curve, the same function. But maybe the way I describe the function can tell you if you were trained T1 or if you were trained in T. And this is all. So even if you have the same function, there are several ways to describe it. And maybe the way you describe it is to leak the information. Definitely, this is it. That's somehow, this problem is very well known in cryptography and it's called the obfuscation problem. This is something that happens, some vulnerabilities that are discovered every day in Windows, and then there is some patches to solve them. So how these patches are created? So of course they are created by designers of Windows, so they are created by using all the information that is secret that is in Windows, and you have to run them. So essentially, better that by running, having the possibility to run this patch, there are no extra vulnerabilities which are revealed by the way the patch was designed. Essentially, you need a way in which you can run a functionality like this patch, but there is nothing that is revealed about how this patch was created beyond the possibility of using running. Actually, by the description, the internal description of the algorithm that you have to run, there is no extra information beyond the algorithms give you as an input versus output function. The description of a patch should allow to run the patch, but without revealing any extra information on the operating system that could help to discover new vulnerabilities. So essentially, that's the idea. So that somehow you can run it, but you need a description of the algorithm, but the description itself doesn't reveal any information beyond the algorithm if you see it as a black box input-output. Actually, having the whole description of the machine, all these thousands of internal parameters, machine should not give you that you need these parameters in order to run the function. This should give you more information about the training set that a black box access to the machine. So this is just a black box, and you can only use it as an input-output relation. So having full description of the machine to run it in your own computer should not give you more information as if you use it remotely. Now, that's exactly the concept of obfuscation. So how to reduce white box description to a black box. Okay, so that's the idea. And this is what I said, that something is irrelevant. Irrelevant means any information in the parameters is beyond the possibility of using a black box. It's not that you cannot obtain by a black box. Any question about this? But to use the machine, black box is kind of the minimal thing you should ask for. That's that we don't have any more information. Okay. Okay, so one may ask, okay, is this really a problem? Okay, the first answer is yes. Okay, so what we did in order to detect that was, okay, we very large COVID database, and then there were kind of patient data, age, gender, blood pressure, blah blah. there was one particular information which is really irrelevant, which is the parity. Okay, it was the day entering the hospital, and we just took the parity of final. And the goal was to learn the probability of death based on these parameters, age, gender, etc. Of course, the parity of the entering the hospital should be totally irrelevant. So we trained some neural networks to try to learn that. Okay, as data, so new some of this, and we got a pretty nice prediction accuracy, 85. But then we try to attack this machine, and by having access to all the parameters, we try to learn, the parity of the day entering the hospital. The way we did that was to create two training sets which were biased. One training set, let's say 80% of the patients you put there enter in an even day, but and vice versa. I was just trying to distinguish training set one from training. And okay, we did it with probability, essentially the same as the bias. Okay. Okay, so this is fun. In the sense that some irrelevant data can be learned by having access to the parameters. Okay, so that's what there is a problem to solve, which is always solved. Questions so far? Yeah, please. And I'm so you have to distinguish whether it's one type of training set or the other. Both give the same prediction accuracy, both give the same black box. Having access to the white box, you can decide which one of the two sets. See these attacks disappear. That you say, okay, because I know the bias in advance, I say, okay, go for it. Know the bias. Learn the bias. Knowing. See, this probably solve using tensor. Something that can be solved. Easy. So, say, learn is the curve of the bias. So this the probability of getting that there is a bias somehow is just really the bias. So instead, of course, close to the field. Okay, good. So by the way we implement the attacks was also training a machine to attack. So somehow protect ourselves. The bias machine to detect. Okay. And there are more spectacular attacks in images. So it's a paper, our paper later, and then somehow also by having access to the data parameters, they managed to reconstruct essentially images that were in the training set. So these below are the images in the training set, and these things are images that were reconstructed by having access to the a lot of information about the training set already. Okay, so which is the underlying problem? Yeah, yes, sorry. No, the other one. The other one. The other one. No. Um, no, sure. That's right. What we did is to train many machines with the first data. All these in another machine. Yes. Yeah, that's right. That's right. Totally right. And the goal was not really to show uh, recent attacks, to show that the information is there. So it was not there, this attack was not realistic. Simply so that the information is there. This is the thing. Okay, so which is again the main problem is that the information of the relevant variable is erased through the neural network so that it does not appear on the input output. There it's not there. Input output relation, the information is not there. You cannot learn. But the thing is, the way in which it's internally erased depends on the not the fact that it's erased or not. It's how it is erased. And this is what our attacks explore. And then, of course, this is very much related to the following. So it seems that then there are many possible choices of parameters which essentially give the same function. Ways of erasing are different choices of parameters that in the end give the same output relation. And this is the question, which are all these possible different? So again, in physics, this is something, it's a name, which are gauge symmetries. Symmetries which are simply internal symmetries, it's an effect, a function, in this case. So the idea is then that neural networks, the key problem is that these gauge symmetries are not well understood or characterized. It's so far. Since we do not know how to erase this information by somehow selecting a particular gauge or so the problem. And it seems now there are results showing that this is something which is very hard. Especially if you have a lot of parameters that have some sensation, then somehow have global minima close to every initial point essentially. Find this gauge. But, and thus, gauge symmetries are much better understood. The reason for that, and precisely the interpretability of tensor networks for code. It's exactly. Gauge symmetries are actually behind such. That's why this has been done. You can exploit that in order to use tensor networks to solve this. So for that, of course, we need to Yes. Two parts. First, part one, only matrix for the states. Here. So we have a nice, I think, nice review article. RMP in 2021. So we essentially try to summarize all the knowledge of the mathematical theory of tensor networks and how it is used in order to understand exactly classify. So, in order to talk about tensor networks, the most important thing to understand is notation, because box-like notation for them. Essentially, a tensor is a tensor. It's many complex numbers indexed with several sub-indices. Vector, a matrix, three tensors, coefficient with three indices, complex. Vector, simply, it's a tensor with one single index. No? A matrix is a tensor with two indices, no? Row and column. So the way to represent it graphically is simply to have some box, some label, and then as many legs as indices. But each leg corresponds to an index. This leg is the index of the vector. These two legs are the row index and the column index of the map. In principle, I could put arrows in the legs so that there is a direction and separate heads and brass, and this is like a contravariant, blah, blah, blah. Tensors. Point of view was just complex numbers, indices. Okay. We have just two rules. So rule one is if boxes together, this is just the tensor product. Now, second rule, if we join legs, this is tensor contraction. But covariant and contravariant is standard basic summation. In this case, it's just simply identify the two indices and sum over. Okay, so let's do this for matrices. I have two matrices, A and B. So then together, these are the tensor product of the matrices. So B. And this is just simply, all possible. Now, four indices, two of the first one, two of the second one, and I have all the possibilities. Indices, no? It's A by J times B R S. No? Sometimes it's called the that's the tensor product. And now I will join this leg with this leg. So actually this means that I will identify the index here with the index here, I will sum over that. So I will identify, okay, this should be a J. So identify the second index of the first matrix, column index, the row index of the second matrix, and I sum over that, sum over J, and then this is exactly matrix multiplication. That's all the rules. That I can construct more complicated. But the two. So let's go most basic tensor, which is called matrix product state. And let's start with the traditional invariant case. So we have like single tensor with three indices, one index top, which I index by I, and then the other two indices. So once I fix this index I, the other two indices are just the index of a matrix. So this three-leg tensor is a sequence of matrices, finite number of matrices. Which I put here, I have a matrix identified by the leg left and right. This three-leg tensor is just simply a finite number of matrices. So index I tells you which matrix to. Okay, so these two type of indices have different meanings. So index pointing up is physical index because it's matrix for the space and quantum mechanical system. This is really physical speed, physical degree. And then these two indices corresponding to the matrix, to the row and column, this is called the virtual index. It's a different dimension, which is called the bond dimension. And this simply is just physical in a sense. This is just mathematical object that encodes somehow the correlation that will be present in the system. Some dimension we can play. Okay, so now let's take this three-leg tensor, this diagram. Graph, which is a circle. I put every graph of the circle. And let's try to see what's that. Because I put first all the tensors together. I have all these indices tensorized. So I have this I1, I2, IN, tensor product of all. And once I fix this I1, I2, IN, they fix. What I have is just matrices. One matrix, another matrix, another matrix. Matrix A, I1, matrix A, I2, A, IN. And I learned from the previous slide that if I put these two matrices together and I join the leg, this is just matrix multiplication. I'm doing is multiplying the first matrix, A1, the second, I2, the last one, and I have this product of matrices. And now with the final matrix, what I do is I contract for that matrix the row with the column. That's the same. Matrix is identifying row index with the column index and sum over that. This is exactly the trade. Okay, so essentially, this object, this diagram, is a quantum state. It's not normalized. So a vector, it's a quantum state. It has exactly this expression. By expanding the computational basis, the coefficients are given by traces of products of matrices. That's the name, matrix product. It's our first lesson. Question about exactly? Okay, we can do the same with automated invariant, just asking that each one of these three-leg tensors is different. It's a mistake. Bracket here, but essentially it's the same thing. If I fix the subindex I1, I2, etc., this is a product of one vector, matrix, 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 vector, which is exactly this thing. Same as before. Now, of course, trace, so at the left-hand side, the right-hand side, I have a matrix in which the row index has dimension 1 here, column index has dimension 1 here, so this is as vectors. So this is a number. Benefit that of a situation in which I do not have the recent variance, in learning, variance is not fast. Then, okay, more parameters to play. I can take all these things different. Okay. Okay. Use these objects for machine learning, but of course they require. So there are several reasons. So the main one is that they approximate well ground states in one-dimensional systems. Also, they approximate well thermal states. But for that, of course, we have to take mixed states. Instead of multiple state, we have to take something multiple operators. Essentially the same thing. But now, sorry, instead of taking just one leg here as a cat, I have one leg as a cat, another leg as a bra here, everywhere. These are operators. Something to consider in it. So, but they approximate well ground state of local interacting gap Hamiltonians in one dimension. This is something that somehow took a lot of time to get formalized. Essentially, in the early 90s, the PMRG algorithm appeared by Steve White, and essentially it is optimized energies of one-dimensional Hamiltonians by searching in the family of multispot states. That way, but it's so good. This algorithm is still successful. Solved all dimensional. Then people try to understand why, and then by mixing, using a lot of ideas from quantum information, people manage to solve that indeed that's the case. So very nicely, because really it's true that all one-dimensional ground state of gap Hamiltonians are exactly essentially mathematical states. Indeed, the bond dimension D that one needs to have a global error fidelity smaller than epsilon grows sublinearly the system size over there. Small. Okay, so essentially that's why so successful. As I said, it's not that they approximate well-grounded states, it's that such approximation can be found efficient. Practice, VMRG, it's the best you can do, but in theory, there are even algorithms that have provable convergence in the sense that know that they can, there are some algorithms that converge into numeric ability. Prove that indeed the problem of finding the ground state of a gap Hamiltonian is simple. Okay, but even more, once you have the approximation of the ground state, then you can use it to compute relevant quantities like some functions, expectation value of observables, etc. It's also important. You need to have those states for something, right? Use them for something. And the idea why it's easy to compute quantities you care about, like expectation value of observable from multispot state, is very easy. So let me just compute just the norm, so expectation value of the n. Same for any other. So then I have to just do the scalar product of the multispot state with itself. So I write the multispot state here. I contract with the multispot state joint, and it's simply just the same multispot state, but with complex conjugate. So this is the tensor network I have to contract. This is a number. It is a number. But this is a number that I know how to obtain, because all I have to do is to follow the rules of the tensor network. So I put all these tensors together. I contract all the indices according to that. Okay, this can, you look at that, may seem complicated, but it's not. Because one can read it. We can have these two objects together as a big tensor with two legs, this one and this one. And see these two things together as a big tensor with four legs, to the left, to the right, so on and so forth. But now if I neglect what is inside, just look at this object. This is a matrix multiplication. It's some object that is contracted left and the right indices with next ones. This is matrix multiplication. Matrices which are a bit larger. Instead of being d times d, they are d squared times d. Because matrix multiplication is extreme. This is very efficient. Okay, I did it just by putting identity in the middle, but I can put any local observable, and it will just change one of those big boxes by putting in between some operator. It's the same thing. It's matrix. Okay, so these three things make matrix multiplication states a very nice family of states, and that's why it's famous and so widely used. Questions? Okay. Now let's go to gate characterization. That is what we care about. So essentially, we know how to characterize the gauges here. So essentially, once we have a matrix plot state, for example, imagine that we take the transition invariant case. So if we change each tensor by another tensor, which is the very same tensor, conjugated by a similarity transformation, so some invertible matrix and the inverse at the other side. And we do the same picture by changing the tensor A, but this other tensor, we get exactly the same state. And the reason is very simple. In each leg, here, I get a y from the left and a y minus 1 from the right. That cancel. For this y minus 1 that I see by hand, they disappear. So this is clearly a gauge symmetry. All the tensors that starting from 1 are constructed in that way is exactly the same vector, exactly the same state. And the nice thing is that this is the only symmetry, the only gauge symmetry. I mean, some gauge symmetries is easy. Difficult is to prove that they are the only one. So essentially, these are the only possible symmetries for the relation invariant. And I will comment on that exactly some subject. Advanced tensor network. But essentially, that's the only. Same for the non-traditional invariant case, but in this case, of course, the matrix and the inverse matrix have some sub-index so that one cancels the previous. It's the same thing. After here, something and the inverse of that at the other. So these tensors are different in each side. Comes from the right, must compensate what comes from the left in the previous. Nice, but why people studied that before? The reason is that somehow this characterization of gauges was crucial to understand the characterization of symmetries states, somehow led to the discovery and classification of specific effects of symmetry of data points. So the idea is the following, it's very simple. So imagine I have the ground state of a Hamiltonian with a symmetry, let's say, CO2 symmetry. If the ground state is unique, the ground state must inherit the symmetry of the Hamiltonian, and therefore, because the ground state is essentially a matrix product state, we should have an equality of this form. It's a matrix product state that is equal to the same matrix product state in which I act with an on-site symmetry everywhere. G simply tells you representation of something. Okay? But now, look, I have two tensors, which is just the basic tensor and the basic tensor with the axiom symmetry that give exactly the same matrix. Because the gauge was unique, gauge characterization, these two tensors must be related by a similarity transformation that depends on the group element. Said that this is the only gauge it's possible for math. That's nice because somehow suddenly we get a local characterization of the existence of a global symmetry. Local characterization of a global. That's very nice. Now one can prove that these objects, are a representation of the group, but a projective representation. And then by something which is called the second cohomology group, that essentially tells you all possible projective representations which are inequivalent relation in which the trivial is a linear representation. And essentially, these non-trivial projective representations exactly characterize the symmetry protected topological phases in one dimension. Tensor networks then is very easy to see how they emerge, and it's very easy to find variants. That's something that comes out of just the characterization of gauge symmetry. Why people study that? nothing to do. The thing is to understand how these things merge, what's the use of that. Okay, so let's go. I should maybe make a break, but I will promise to finish. Okay, so let's go back to privacy machine learning and see how to use this characterization of gauge symmetry to raise information if we do machine learning based on tensor networks, in particular multiple steps. So there are two possibilities to erase the information present in a gauge. One is to fix a gauge. Among all possible y's, y minus one and half there, let's choose one. This is a non-trivial thing. And okay, I know how to do that, but I will not talk. One which is nicer, simpler, which is sampling the gauge uniformly. Know all possibilities that gives exactly the same state, same function. If I sample uniformly over those things, whatever information is in the gauge vanishes. Okay, so we'll focus on the first one. So we need to sample the gauge uniformly. So imagine that we train a matrix for the state based on some COVID data to represent a function. Get a matrix for the state, and we know that there are many others which have the same function. But the nice thing is now we know which are these others. These others are exactly those which have the same tensor, but with the possibility of conjugating with invertible matrices, so elements GLs and the general linear group, so it's an invertible matrix. So now we need to sample in this general linear group. That's hard. It's uncompact object. You have to sample them. And let's have to sample uniformly. So okay, so how do we solve the problem? The problem is solved by the existence of something which is called a canonical condition. So with a lot of generality, one can assume, it's a way to do that these tensors fulfill a nice condition. Essentially, that they represent a quantum channel. They are the cross operators of a channel, in particular this property. Some joint times non-adjoint is the identity. If I impose this canonical condition, then the gauge reduces from being just invertible matrices to being unitary matrices. This is very nice, because the unitary group is a compact group. It's a measure, which is the hard measure, that precisely formalizes what it means to sample uniformly. You can sample. It's crucial to make this reduction from GL to invertible matrices, that we have a way to sample. In the case of multiple tests, one can go further and add other canonical conditions, something which is called the left canonical form. Now the gauge is even simpler. Many copies of U1. So sample because it's called R measure there, which is okay. So does it work in practice? And the answer is yes. So if there are many things here, but you just have to read the neural network that was the one before, this blue, and then the one in which we sample, which is this two. But in any case, they are essentially 50%. So there is no. I think it's exactly no. This is the red. It's canonical plus sampling. So it's the red. So essentially below, and then of course some ups and downs, but this come of course fluctuations. But essentially, as you see, no matter which is the bias, you don't see anything at all about the irrelevant parameter, this parity of in the hospital, if instead of using neural networks, you use tensor networks. And the reason is that only for now, it's important, but if we don't sample we just use the canonical form. So sorry, we don't sample, we just take MPS. You can read everything also. So the information is in the gauge. This orange thing is just training with matrix fault states, but without doing all these things to erase the gauge. And you see that there is information in the training set about of the training set in the gauge. So indeed we obtain it. Okay? But once you sample, first in canonical form, sample and sample, all this is erased totally. Now this confirms the idea that in these gauge symmetries, both in neural networks and matrix fault states, indeed you can read irrelevant information from the training set. But once you solve the problem in the set, you fix the gauge. In the gauge is in our case is the purple, so it's also 50%. Or you sample the problem is solved. Shows that essentially if one manages to find a way to sample the gauge neural networks, one could also solve the problem.
So you have some very something.
Yes, this is the canonical form without sampling, of course, yeah. So this is going from general linear group to linear group. Already there, of course, you are reducing the gauge and sample you are reducing the
and we're talking about this yes, but so in the neural network. Yes.
It's a very good question. So there's a very good question that is very much in the final slide about future directions, and there's a talk of Jose Pareja today. There are two possibilities. One is you start with a neural network, rest from matrix. Okay, that's something that you're doing now. Some of that. You here we train directly at matrix fault. Directly train the state. Not that we first do a neural network and then we rest. Let's train directly at it with. No. In this case, it's multiple so much. Something not. Still, you get a pretty good say wouldn't say it here, but the accuracy in the prediction doesn't decrease. The network or your physical side. Essentially, the dimension. Exactly. Sorry, can you repeat how do you go? Yeah, sure. Essentially, so one can impose without loss of generality this condition, meaning that you can select by playing with the gauges you have. You can select. So essentially, you can take you have a very positive map. This is the map in which x goes to this x in between that. Then by playing with the gauge, you can force that this is the identity. This point is so you can select the loss of generality a gauge with this property. And if you enforce that you only care about matrices with that property that represent the same state with that property, then they must be related by unit. This is if you reduce the problem to matrix for the state in which the tensors, all of them have this property. So loss of generality, you can assume it. There is a particular choice of gauge with that property. It's a very good question. We are now playing with many data sets. Our guess, so we have, in principle, whatever is in the gate should not appear. It's a theorem saying that is the only possibility. Of course, epsilons matter. Close enough, but still, blah, blah, this is an exact result. And all the results we have with epsilons are not strong enough to guarantee them. We expect the same result. Now, example that we talk about to figure out it's a general feature. We think so, but okay. So we simply choose, we sample one of those U's at random, and we change the A by the U daga AU. Sample it with that. Each one is an independent, each one is an independent.
Right? By just using
Okay, so question is, can one extend? Okay, so problem with MPS is that it's a very one-dimensional thing. So far, and also we talk about that it works very nicely with data sets that or are not too big, like hospital data, or they are one-dimensional, voices, speaking, sound. And very nicely there, but things that are more like two-dimensional, like picture, happens to be the same with called math with system. Math is what the states are not. One maybe needs to go to something which is more two-dimensional. There's networks which are two-dimensional, and they are X. And the problem is that they are much harder to deal with. And second is, but even before that, can one extend the results? Perhaps, I mean, characterizing the gauges, the possibility of sampling of before practice. Basic theorems that behind method can be extended to. That's how we talk now. So we need two things. A good characterization of the gauge symmetries. Again, this has been done and it's relevant also by the same reasons as in 1D, trying to understand symmetries in systems. And also a canonical form which reduces the gauge from invertible matrices to unit. Okay, the first thing is something that did already in 2010, just for lattices, and for arbitrary graphs later extending it. And okay, in order to reduce vertical to unitary, something that recently that paper nice because I mean this is the first rigorous canonical form for PEPs in any dimension. And as I said, this is something that was not clear even to exist. Something I'm saying. So that's the second part. Last part of the talk. Okay, so now we are experts in this tensor notation. We want to do something in 2D. We need 5 legs. So we need one physical leg, which is this arrow, like pointing out of the screen. And in order to avoid super cumbersome notation, this arrow will be just this red dot. Red dot means an arrow pointer. And then I have arrows which are virtual that gets contracted through the lattice. So now I have this 5-leg tensor, I put it in a lattice. I fix the boundary conditions, either by periodic boundary conditions or by vectors or whatever, and I have here a state. If I move the degrees of freedom from the boundary, the only indices that are open are those red arrows. It's exactly a state that lives in the tensor product of Hilbert space here, etc., which is a many-body wave function. It's called a PEPS. So there is a nice, problem somehow in order to find a canonical form for PEPs. And the thing is that in 2 dimensions, any problem you may think of is in general undecidable. In particular, given a tensor, it's undecidable to know whether the associated vector, we take periodic boundary conditions here, is 0 or not for all tori. But this is exactly the problem with the gauge. No, of course, there's a very easy way to represent the 0, which is putting the tensor equation. If I have another tensor, it is undecidable to know whether it represents the same as the 0 or not. It means that the gauge itself is undecidable. It's undecidable to know if this tensor is represent the same state as this other tensor. And then decidable, of course, the hardest possible thing I can imagine. It's in the algorithm, no matter how inefficient to solve. So essentially, this is like a no-go theorem. And the reason why this is undecidable is that it's easy to encode tiling problems into PEPS problems. Tiling problems. So essentially, this proves that gauge symmetries in PEPs are undecidable. And since a big abstraction to solve our problem, but okay, it is not. The reason is that even if these undecidable instances exist, they have measure 0. So the generic tensors don't have this problem. So essentially, this is what we prove. We say that two normal tensors, I will not define what is normal, but let me just say that normal are generic. Means that the complementarity of the normal tensors have measure 0. And a submanifold. So essentially, whatever numerical algorithm you design, you will always get normal tensor. Never get non-normal tensor until you lose sense. So, and for normal tensors, we have the expected gauge degree. If they define the same pairs for all tori, they must be gauge related. The two tensors are related by one invertible matrix in one horizontal direction, a different one in the direction. The same result is true in the graph. Okay. So now, the key mathematical thing here is to use something which is called geometric invariant theory, which is essentially the theory that studies how Lie groups act on manifold. The next thing is one can see this as the action of a Lie group, which is GL cross GL, into the set of tensors, which is just acting by conjugation. Manifold in the set of tensors have an action of the Lie group, GL cross GL, which is this action. A pair of invertible matrices YC goes to that object. And this defines the orbit of the tensor as all possible tensors that are obtained in this way. Actually, all possible tensors which are gauge related. Actually, now, gauge invariant somehow language is talking about orbits. Okay, so let me now a small bracket and try to use this to comment about how to prove or formalize the fact that in one dimension, this is the only possible gauge. So that's the question. I have two different tensors, define the same matrix for the state. As I said, it's a clear sufficient condition that this is true so that this is true, but I would like the other implication. Necessary condition. And the answer is no, it's not. And then I give you just a very simple example. I give you two representations by tensor networks of the GSC state. GSC state is all zeros plus all ones. There are two possible ones. One given by M0, all zeros, and one to the all ones, which are these, and another one like these ones. So the idea is very simple because both are upper triangular matrices. They keep the upper triangular structure. But once I trace here, whatever is in the upper right corner does not play any role. So whether I put a 1 here or a 0 here is totally irrelevant, as long as the diagonal is the same. Upper triangular matrix. So they define the same matrix called state, but it's not difficult to show that they cannot be related by any similarity. Okay, but I told you before that this is the only case. They are almost equal. So if one allows limits, not just gauge transformation, but gauge transformation and limits, then they are the same. So you can obtain the green from the orange by taking the limit of this similarity transformation with this matrix. In order to have, so this solves this problem, but this solves all examples. So now we have to talk not about orbit, but about the closure of the orbit. So whatever it can reach by doing conjugations and limits. And now we say that two tensors are gauge related if the intersection of the closure of the orbits is not. I can go the same place from one and the other by doing symmetric transformation and the theorem is that two tensors are gauge related with this definition of gauge allowing limits if and only if they represent the same matrix code state for all L. So this is the right notion of gauge is allowing for similarity transformation and limits. 1D is okay, so listening to D. So we say that two tensors are gauge related again if the closure of the orbits have a non-empty section. And with that, we can define it's called this minimal canonical form. Okay, so because of normal tensors, this is not a problem because for normal tensors, the orbits are closed. With normal tensors, the orbits are always closed. Nice to pay to D that we cannot cover all tensors because of this undecidability, and if we reduce to normal tensors, somehow closure problem is not needed. Okay, so now problem again is we have these invertible matrices and we want to reduce to unitary matrices, a canonical form, and this is what we call the minimal canonical form. Essentially, what we do, we consider this tensor, okay, and we consider all elements in the orbit, also, and we minimize the norm, the Hilbert norm. I see this as a 5-party state. Each one of these objects is a tensor product, and they come the Hilbert norm, the usual Hilbert here, and they minimize that norm in the orbit. The object that minimizes that norm is what they call the canonical. All the elements in the orbit, they minimize the norm. Okay, and then it has very nice properties. And all these properties are consequence of results in geometric invariant theory. So also new property 1 is that this is unique up to unitary densities. This means that essentially, if I consider elements, all of them in canonical form, they represent the same state if and only if they are related by unitary densities. That's what I want. Invertibility. Second, it can be computed efficiently. It's nice. There are two possibilities: doing just geodesic gradient descent, this is polynomial one dimension of the error, or doing some second order method, which is polynomial in the exponential of the one dimension, so it's much worse with the one, but logarithmic in the error. It's much better with the side. And okay, this is an algebraic formula which characterizes being in minimal canonical form, and this is useful to check because many concrete tensors are already canonical. So that's a bit the solution. Let me say promise to earlier, so let me see now. So this is a potential solution to obfuscation in PEPs by sampling. It's compute a minimal canonical form. So let's say train a PEPs, some data. That's the hard part because there you have to minimize a variational family of PEPs, some energy function or loss function. This is not easy, but expect this. But let's assume we already have this. Have a nice PEPs, approximates where the function I want. Then there I compute the minimal canonical form, and that's possible because of efficiency. Now, since it's unique up to unitary basis, then what I can do is to sample uniformly the Haar method because I know that the only gauge is this unitary gauge. This is all the potential leakage should be there. Okay, all this minimal canonical form I did for a traditional invariant case for simplicity, but it can be done for the same. As I said, this needs to check if it works in practice. So, yeah, as I said, optimizing this in practice is much harder. It's the roadmap, I would say. So let me finish. Tensor networks have a good case characterization, which is usually called in tensor network theorem. The reason is because it's super useful. And it has nice privacy implication, as I illustrated. So as I also said in the talk of Jose, maybe he talks about other nice implications of tensor network properties for machine learning. Okay. But there are other nice implications of the minimal canonical form even within from math. And I don't know if Paula will talk about that or not. Okay, she will not, but you can ask her. And that's it. Thank you. I was waiting something. A very good question. In principle, here the nice thing somehow is the size of the unitary you have to sample are very small. On the dimension, which is something that it must control somehow because otherwise the designs are nice if you sample a very big unitary and you make it to approximate like. This is not the case here. At some point, one needs to do something a very big unitary, of course. The thing so far, the dimension you have, you can just sample the Haar measure by hand. So yeah, okay. So essentially, what we did is just to illustrate in one example the fact that there is a potential problem, a potential relevant information if you have access to the parameters of the machine. It is to illustrate in one example this happens. Relevant information is present in cannot claim that this happens, but I think really this is something that. In that case, we did this example because it was crystal clear that it was relevant. Something that are maybe relevant, but not that much relevant. Still, you get a lot of information that information that maybe you shouldn't get. I mean, there is not just whites, but just put this example as a illustrate that there is a problem careful about. External example, and then tensor networks could be one of the solutions. But as I said before, answering the question, still need and we are doing more detailed analysis with different data sets, notion, degrees of irrelevance and all that to answer this question. Is working.
About usually we don't exist in one and then yes in one day. All the other parts so they don't matter. Then a lot of values just clear. Where here it's average and opportunity types. It's
But once you are in canonical form, geometry does change that. This property of canonical form is exactly the property of having an isometry. Essentially, if you have a quantum channel, times the relation of a quantum channel is an isometry inside the isometry. So once you have this is exactly the property that these objects are isometry. Because by putting unitaries, you keep unitaries, you keep them. Maybe question. But our paper is this not our paper. And this is done with a network. So to sample the gates, you should do that with first because of and with the way the attack here is totally different. Nothing to do.
They are all for different features, but they are also, for example, regular booking.
It's a good question. I don't have. You will know and say this is something.
It's very difficult. So are there more? So if not, then we just have the back the 30 minutes for the next section of
Claro, bueno, sí, no.
Pero yo aquí me interesa.
No sorprende, sí, claro, claro.
Porque
Una vez o dos, sí.
yo creo que es. Claro, tiene que ser de algo.
Pero en
No, sí,
sí,
dicho la de Alex, quiero por lo de los y la tuya. Ya está, pero me gusta.
Carlos.
ves, encantado, muy bien.
Sí, no, perdón, que te iba a contar porque tenía mucho que
Sí.
Te puedo responder
Sí, además fue porque aparecía justo universitaria, para mí tranquilamente, llegó al metro, la línea así se está cortada. Me iba a hacer descargar, hay que del metro cascar en el túnel. Un chico que me ha jodido.
Era por la
Guardado. ¿Dónde la guardar? En el escritorio, ¿no? La siguiente sí. Ha dicho que ha actualizado. Han subido las dos. Ahí hay 5. ¿Cuál es el orden, Juan?
preparada. Al rato.
Para ver el tiempo. Quemo la... Te meto la cara en primera. Está en directo. Ayuda al personaje.
La dejo ya. Welcome back, everybody. Now we are going to have the next session, which is about contributed talks. First, I would like to say that afterwards, we are going to have a group picture of the workshop. So for lunch, please don't go because we want to take a picture and then we will have time for lunch as usually. So now let us start with the first talk, which is by Juan José Rodríguez Alavero from IFF, the Institute of Fundamental Physics here at CSIC. And he's going to talk about Chebyshev approximation and composition of functions in matrix product states for quantum-inspired numerical analysis.
For the introduction. So in this talk, I want to explain a few methods to encode functions in log states using Chebyshev. So this is a brief outline of what I want to talk. First, I want to introduce the background, mainly what is multivariate numerical analysis and the course of dimensionality, and the techniques based on matrix product states to the methods used in the work based on Chebyshev expansions, numerical results justifying the algorithm. So first, let me talk about multivariate numerical methods, quantum-inspired numerical. So in principle, multivariate numerical analysis involves a collection of methods that can be used to solve numerical problems. For example, if they are multivariate. Some examples of these methods are for integration, Fourier analysis, eigenvalue problems that finding the largest of eigenvalue of a vector or matrix, or solving partial differential. And these are some examples of popular numerical methods, such as quadrature methods, finite difference, etc. The problem with those methods is that they usually operate on multivariate functions, which are represented by tensors. So following the representation of boxes and indices shown in David's talk, a vector can be represented in this form, which has a number of elements proportional to the density of x1. A matrix can be represented in this structure, has a number of elements given by the product, and etc. for higher dimensional functions. So the tensor, the size of the tensor for m variables grows exponentially with the volume, with the number of variables, and this means that the volume is exponential and there's a curse of dimensionality. So this can be tackled using techniques, quantum-inspired techniques for quantum mechanics. For example, matrix product states, which are efficient ansatz of quantum states which have low entanglement. In this case, as David explained, the amplitudes of the tensor are given by a product of if they are low entanglement, well, as we can see, the exponential number of elements is broken into a polynomial number, and if the state is of low entanglement, this value, the bond dimension, is bounded, and this leads to an exponential. This can be applied to functions by discretizing each dimension into bits or binary variables from x to s. Now m variables becomes n times m bits, and encoding this tensor of coefficients into a matrix product state. This breaks down the course of dimensionality exponential scaling to a polynomial form as long as the bond dimension is bounded as a maximum value or does not grow too quickly, the dimensionality. This is also called the quantized tensor train. So the good thing about quantum inspired numerical methods is that they are very efficient. And for example, for the previous problems that I explained, direct integration, analysis, eigenvalue problems, they are corresponding quantum inspired methods that are very, very efficient. An example here is multivariate integration. It compares Monte Carlo methods against quantum inspired methods based on tensor trains. You can see this is the error against the time needed. We can see that the exponential given by tensor train or quantum inspired methods is exponential. This is a very large improvement, both time and memory. This can lead to a large advantage. And finally, I want to mention that to take advantage of these methods, the function needs to be loaded in matrix product state, and this is not easy. It can be challenging. Standard approach is based on a recursive decomposition, the Schmidt decomposition, or by decomposition. The problem is that it acts on the whole tensor. So again, you need to have it in memory to decompose it. And this is always very hard to do if the number of dimensions is large. So this cannot be done in practice often. And there are some alternatives that tackle this issue. For example, multi-scale interpolative construction, which is fancy name for a Lagrange interpolation of functions in polynomial interpolants, tensor cross interpolation, and the method proposed in this work with its iterative expansions of polynomials in the Chebyshev base. So mainly, first I want to introduce the technique that founds these methods, which is Chebyshev interpolation, which essentially is finding a polynomial that approximates the function. And a very convenient basis for this is the Chebyshev basis, the basis given by Chebyshev. So essentially, these polynomials are orthogonal and have a three-term recurrence relation. And the information from the function can be extracted by evaluating the function on a limited collection of nodes, such that it can be very efficiently approximated by an expansion on. So this is the method that justifies the adaptation to matrix states. In general, the adaptation from the vector or tensor-based Chebyshev interpolation to matrix product states, which is much more efficient, avoids the curse of dimensionality, is straightforward as long as you can approximate linear combinations between matrix product states, multiplications, and you can avoid a growth of the bond dimension given after every operation. And this can be done by a variational approximation of the linear combination and simply by element-wise multiplication of tensors for the multiplication. And then you can approximate the expansion given for vectors, which is this one here, the case of matrix product states, by summing up these states corresponding to the Chebyshev polynomials, which actually can be evaluated from a three-term recurrence. So in principle, this can be, and also there are some optimizations that are done in practice, such as clean-share evaluations. But in principle, this is the general idea. And the good thing about this framework, about the approximation function this way, is that actually it does not only allow you to approximate functions, but in general allows you to compose functions on matrix product states, which can be advantageous to manipulate initial state non-linearly, and also to load multivariate functions that have a simple enough algebraic structure. So the general idea is that you can have an initial state, which can come from, I don't know, any other algorithm, such as a partial differential equation, etc., a matrix product, and then you can manipulate it. You can apply a function to it. You can apply a function to some collection of tensors, etc., and manipulate it. And also, it allows you to encode multivariate functions by constructing an initial state that corresponds to the discretization of the space in a number of variables, and then apply a function to it. Allows you to encode multivariate. And this initial state can have its qubits in different orders, given to a place to an equivalent representation that can be much more. So now I want to show a bit the numerical results obtained by this method, mainly to encode, load a collection of univariate and multivariate functions in matrix states, achieving in some cases exponential advantages in time and memory. And also I want to compare the results with the state of the art, mainly with the two other methods I explained before, that is multi-scale interpolative constructions and tensor cross interpolation. So for the univariate case, we want to test loading these four functions, which is two analytical smooth functions, the Gaussian and an oscillating functions, and two non-smooth functions. For the non-smooth function, the method is not going to work well because the polynomial expansion is not accurate, but for the other two, it's going to be accurate. And we want to consider the effects of the size of the initial state and the number of interpolation polynomials used in the maximum error, complexity of the state, and time needed for the, the general setting for the experiments. In general, first we start encoding these four functions for an initial condition that has a different varying size, which is given by the number of qubits, and which is where the number of points is the exponential of the 2 to the number of. And we can see that the error is stable and converges asymptotically to a given value, and the maximum bond dimension of the function plateaus on a value that does not depend on the system size and only depends on the function. This implies that the polynomial interpolants are of low entanglement, the corresponding quantum state, and also this implies an exponential advantage in memory over tensor representation, because you can grow the number of qubits, the memory needed to represent this state grows linearly with the number of qubits, but it does not grow exponentially with the bond dimension because it is bound. So this is, and also the time required grows sublinearly with the number of qubits, which is also advantageous because it implies that it grows sub logarithmically with a large n to the small n. And this again implies an exponential advantage over a Chebyshev expansion of a vector, of a very large vector, which is also an advantage. And with respect to the accuracy of the interpolation given by the interpolation order, we see that it converges according to theory, and that is exponential for analytical functions, and algebraically for functions with some derivatives. And this enables the interpolation for large approximations. The advantageous properties of this algorithm is given because the bond dimension structure concentrates along a few qubits and not along the whole matrix product state, so the simplification and operations are efficient. Sadly, even though the method is performant, it does not beat other the state-of-the-art algorithms such as Lagrange and tensor cross interpolation for the univariate case. However, it has advantages. And for multivariate functions, we consider these two functions, a product Gaussian and a squeeze Gaussian, for dimensions from 2 to 10. So very large, moderate large dimensions, and each dimension has 1 million nodes. So the total space is very large, actually, 10 to the 60 elements, during both the serial and we can see that the error is again, it converges close to matching precision, even though now it degrades a bit with dimension, as we can see here, but it converges. And also the method requires polynomial resources with respect to dimension, which is also an exponential improvement over a tensor interpolation. With exponential, as long as the system is well behaved, for example, the qubit order is appropriate. And again, this is given to an advantageous bond dimension structure in both serial and inter. And now the method compares well with the state of the art. As we can see here, the Chebyshev algorithm, which is defined here, is more performant than tensor cross interpolation, which is marked here. requires less time for the given or error, and also it requires much less function. Instead of several million, only a few hundreds. So in conclusion, I would like to mention that the proposed MPS Chebyshev algorithm allows to compute functions on initial states, and it can be applied for loading functions and also state manipulation. It requires polynomial requirements in both cases, and it compares well with the state of the art, even if the numeric case is not much faster. And as an outlook for future extensions, we'd like to apply this method to operate and some more. So I would like to thank the co-authors of this work, which is Paula Garcia Molina, Luca Tagliacozzo, and Jose Paul, which are members of the QINFO group, and also acknowledge Alex and Ernest for.
Thank you, Juanjo. Are there questions?
Hi, thanks for the talk. I would like to ask a couple of things about the functions that you're trying to fit in this talk. So you were saying that there are two of them that are complicated in the sense that I think, well, the step function and the other one, which I think it would be one sine of 1 over x, something like that.
So the complicated functions are the absolute value with the orange and the green function.
Okay,
The
what about
oscillating function is analytical and it converges well to the because it is smooth. Even though it's very oscillating, its derivatives are smooth. So
which function is it?
the red one
No,
is
but
1
yeah,
over cosine of x squared plus epsilon, small epsilon. So for epsilon equal
okay,
to 0,
the epsilon is what makes it smooth. So it converges well in the limit of asymptotically many resources, right?
no, I mean for a large enough interpolation order, which can be around 1,000. May seem like a lot, but in practice it can.
In that thing in practice, that thing works better than just the absolute value.
Yeah, sure. Because the absolute value, even though it looks much more well behaved, because its derivative is discontinuous, it first its second derivative, it well, the second derivative diverges. It is, according to interpolation theory, worse to approximate. We can see it. This would be the error for the red function, this oscillating function, and this would be the error for the. This is how the oscillating function converges exponentially for a large enough order, while this absolute value converges algebraically. For a large enough order, it does not.
I understand the argument as asymptotical regime for analytical reasons.
Yes.
Practical reason, it's very surprising, but we can discuss about it later.
Okay, sure.
So thanks to Juanjo again for his talk. So the next speaker is Julio Camilo from Universidad de São Paulo and Universidad de Granada, and he's going to talk about estimating the volumes of correlation sets in causal networks.
Hi everyone, let me know if this is not loud enough. Okay, thanks for the introduction and thanks for the organizers for having me. It's a pleasure to be here. So as Paula said, I'm Julio. I'm currently a postdoc at the University of Granada, where I work with methods to improve classical simulation of quantum circuits. But today, actually, I'm going to talk about part of our work resulting from a collaboration during my the last year of my PhD, when I was still part of the University of São Paulo. It was a collab with my friends Pedro, Davide, Rafael Rabelo, and Rafael Chaves, and in which we used the idea of estimating the relative volumes of typical correlation sets in causal networks to analyze our capability of detecting non-classicality if we consider special features into the right? But before doing so, I want to do a quick review on causal networks. For those who are not familiar with, it's a powerful framework to deal with systems that you can model with random variables, and to which you want also to introduce some notion of cause and effect between the variables. It's vastly used outside physics, but here, of course, we're going to attend ourselves to physics. And in physical systems, I mean, uh, just to give an idea, it's quite easier to understand. So by networks, you just have to understand as graphs, so nodes and edges. And by causal, you should understand as a way of directing our graphs motivated by causal influence between these variables. So in physical systems, you can essentially have two kinds of nodes. One of them is those that we associate random variables to things that we can observe or have access to the lab. So measurement choices, or simply our inputs, and measurement outcomes, or simply our outputs. And the other kind of node that you can have are this one um, that we associate to things that we cannot have access in the lab. So surprise, surprise, we call it like hidden variables or latent variables, or sometimes source of classical correlations. And of course, we have the edges, which here are just exemplary ones. But the idea is that if a variable is supposed to have a causal influence on another, you draw an arrow from that to the other one. The initial one is called the parent, and the variable to which it points to, it's called its child. Right. And what's the goal of this framework? Is simply to answer a question. If I give to you a set of correlation, or in other words, a probability distribution of your outputs conditioned on your inputs, is it compatible or classical with respect to a given causal structure? And to answer this, we essentially have to test a condition, which is called a Markovianity condition, which essentially says that if this probability distribution is compatible or classical with respect to this causal structure, then you can decompose it as the product of the probabilities of each observable node conditioned on its parents, and you just have to sum over the latent nodes at the end, which in our simple example is given by this expression, which we recognize as the probability, the equation that shows probability distributions that are compatible with local correlations in the simplest Bell scenario. Cool. A second ingredient to understand what this analysis that we want to do is the idea of estimating relative volumes, which is actually even easier to understand than the second ingredient. And okay, yeah, essentially you start from this big set of possible probability distributions for a given set of inputs and outputs. It's from a simplex, let's say G, to which you can associate a volume Vg to it. And we are interested in a subset of this big set, which are the set of probability distribution that satisfies some restriction R. And we can also associate a volume to this subset. And the idea that we want to use is that you can compute the fraction or the relative volume of this restricted subset. It can be estimated by simply sampling uniformly distributions in the big set and checking satisfiability with the desired constraint that you want to consider. So typically, to give an idea, it's common to consider probability distribution that satisfy this condition that are non-signaling, which in our previous example just means to satisfy these equations here, which I'm essentially saying that the marginal probability distributions on the outputs of sides parties A and B does not depend on the choice of measurements being made on party X and Y. And just to give a few more words on this, essentially, one interpretation when you don't have this satisfied is that basically you are allowing correlations that can come from theories that are superluminal, for example. And what we wanted to do in our work, one of the things that using this idea of relative volumes, we want to look into the set of non-classical correlations in a given causal structure, analyze its behavior when we consider special features in our protocols to classify probability distributions as classical or not. And these special features that I'm talking about are two. The first one is independence of the sources of classical correlations. And the second feature is the possibility, the idea of considering interventional data and not only data that comes from purely observational protocol. Cool. To address the first feature, we consider this scenario, the so-called bilocality scenario. It is given by this structure here. We have three parties, A, B, and C. Parties A and C are allowed to have inputs, X and Z. And we can send signals from B to A and C too. And the idea is that we can consider two independent sources of classical correlations there. So essentially, if you have some, we say that if you have something incompatible with this causal structure, we call it as a non-bilocal probability distribution, motivated, of course, by the case of the Bell non-locality scenario. So you should have this in contrast in mind with this possibility, which is considered compatibility with the idea of having only a single common source of classical correlation between these outputs. And what we essentially wanted to do, sample from non-signaling correlation distributions given by these scenarios. And it also have to satisfy this condition of separability between the parties A and C, which is a consequence of the framework. And once we have sampled probability distributions from that big set, we looked into the non-classical ones when we take into consideration the idea of independent sources and when we do not take. And the idea is that if you take into account that you can have independent sources of correlations in your setup, you can increase the relative volume of non-classical correlations by a reasonable amount. So it goes to from 2.4% in the case you consider the possibility of only a single source, and more or less 33% when you consider the possibility of two independent sources. Cool. For the next feature, we use this so-called Evans scenario, which is more or less like the previous one, but now without inputs. And okay, the idea in this feature was to take advantage of the fact that signals can be sent from party B to parties A and C to add an extra layer of test of classicality for the probability distribution that we had in hands. And what's the way to do it? Essentially, is to take a, let's say, more active posture in the protocol and collect extra data from interventions being made and the mechanism working in the party B in the middle, essentially to enforce an output and see the effect of this in the parties A and C. And the idea is that we want to reject observed probability distribution as classical if the marginals in parties A and C disagree. The fact that, when you intervene in the system, if it causes some effect on the marginals on A and C, we consider this as non-classical, and we want to see the effect on this on the volume of the set of non-classical correlations. So essentially, we sampled non-signaling distributions in this scenario, and what we got is that when you take into consideration again um, this posture in the protocol, you can go from a set of non-classical correlations that represent more or less 0.12% of the big set to something that represents something more close to 15% of the big set. So the take-home message here is that we can increase our capability of detecting non-classicality by, for example, ensuring that we can have independent sources in our setup. Your setup is such that you can consider the existence of independent source of correlations. And if you take that into account, and also you have a different posture, like, for example, taking interventional data, so hybrid data, not only by observing your correlations, but also interfering in the mechanism of the system and seeing the effect on the other parties, you can increase the capability of detecting non-classicality because essentially you increase the space of available correlations that you can have access. So if I said anything useful to you, or if you see yourself interested, I invite you to read the full paper in which we have also discussions on the quantumness of non-classical correlations in these tripartite causal networks, and also on methods to test compatibility with the causal structure, the current ones. But if you prefer, you can also ask questions. But before doing so, I want to show our gang there. Granada, we essentially have three main investigators there: Hara Juana, Michaelis, and Daniel. And we essentially work with quantum info, thermo, computing, and foundations. And here in the workshop, aside from me, you can also find Alvaro walking around with his blue necklace and Anna too. And that's all. Thanks.
Thank you for your talk. Are there questions? So I have one question. This was like very theoretical, so I wonder what are the applications? Can the setup be used in practical?
Yeah, that's a good question actually. Not like a experimentalist, but I mean, at least the idea of taking interventional data, I think it's something that can be instead of. I think now the idea of having independent source of relations, I would say that I mean, having in mind, for example, the situation of the Nobel Prize, for example, you need to consider a lot of things. Have no test of non-locality, and that's hard to do. And I don't know exactly what would be the consequence once you consider that like your set that you can only like you think it consider.
So thank you again for. Now let's move on to the next. Okay, now we have José Ramón Pareja Monturiol from Universidad Complutense de Madrid, and he's going to talk about tensorizing high-dimensional density.
Hi, thank you for inviting me and organizing. Yeah, I'm going to talk about this in high dimension. I guess about taking functions that represent and giving them a tensor network. If you have feeling like this is quite similar. But in our case, because we are treating high dimensional, we will requirements make some techniques that well so at this point, I guess we just a quick for me for this purpose tensors first. So I will treat the legs in a very manner. I don't really care if I put them up or down sets. If you see something like, you can say this is a high-dimensional tensor or a vector in a high is a matrix acting between high-dimensional. That will be. Tensor networks are just tensors, and these are useful. They allow us to do numerics very quickly, but also theoretically they allow inner things with the component, like in the case of can very easily see. So the tensor and way to get the kind of function I have in mainly these two cases on and is machine learning model. And how can we give a tensor network already trained? So to develop a technique to extract this without further optimizing. Want to avoid training, and also for two cases, machine learning models, they are in a regime high-dimensional space. There are two cases where I have huge space. Here I have a machine spaces. The space of possible images is exponentially large. These exponential spaces, almost all images are not faces. So I have extremely large space full of zeros, and this is sort out. Or we delve into we try to talk about techniques, well-known techniques that are used that can be applied directly. First, the most handy tool we have is the decomposition. If we were in a regime of with just a few legs in go from the tensor to an embedding, just doing with this. The problem is marginal cost. This scales the size in our case, the dimensional case. Not efficient, but still, this video is something very useful because, in some sense, discloses the internal information structure that are really accurate intermediate dimension. This is inefficient, but this issue randomize. I assume I have my what I can assume is the dependent. What I can do is well, just apply a random projection to a smaller dimension bit greater than d. And if assuming actually that the matrix was projections and then applying bad projections, have a quite accurate approximation. Now what we can do is apply this to the projected matrix, and we're working in a low dimensional system. The SVD is efficient. Is now inefficient. Is actually computing that. We will see that find some projections can be, but for arbitrary random projections, we are still computing a matrix exponentially. So last idea behind being used to create these projections that are efficient to compute from the cross interpolation technique to decompose. But where matrices that form post come directly from a good set, columns and rows. This means that the intersection matrix columns and it's a high volume. So the key idea of shelves not just a submatrix of your matrix that behaves well. We can be able to there's recover the behavior of the whole big matrix just by looking at its will behave. So the technique to try to do let's follow. If we assume yes, then we can do these projections. You can find this. You can random projections, space defined by the goes from dk to m, and nodes m. The difference to go from one place to the other is just k. Finds a set of equations that get find. What we do is find this. We don't know. Here's representation, so to apply the equations to the original. With this, we can solve to get, but this also requires extra steps. Each of these equations define, but all the open legs tell us that have an exponentially equation. Many more equations that variables can also project to also a small. Now, fine, that the equations we can solve more. Also, you can extra one. These projected matches take an equation to find actually where the bond. We can define the same. The method is called sketching because it is you are kind of find left this inner record. A sketch of the. Oh, everything here uses techniques for case. Still inefficient is projecting. The add here is the external. And assuming we are distribution, we can do is project or structure find by some samples. In the case of ground states, we can sample functions. In the case of we train the machine learning, have training point, can use this. Actually, this kind of projection you don't have to compute this contraction because entails just defining this matrix that you only have to evaluate the function n squared. And from this to matrix, this is we can and next step and now efficient. So try this first, just a sanity check, something that we know as an which is AKL exact MPS. So see evaluations, yes, and try apply this exactly the same. And finally, our first goal, train neural networks. These are models with just a small drop in the accuracy. It's all now.
Thank you. Do you have any questions? So I was wondering about the application technique because it's quite complex and in general people use TT cross SPT. So if MPS are similar, so the matrix data is still better to use only for large dimension.
Yeah, I mean, kind of problems we have. I didn't mention can also can only feel uh, can
There are
So thank you for your talk. I wonder how could this be applied for quantum many-body problems. So you sample a quantum state, which its amplitude, and then construct its MPS representation. Well, yeah. So how could this be applied for quantum many-body problems?
yeah, well, already have like the MPS sample from. I think we are trying to learn the system. Monte Carlo techniques, they network, and yeah, once you have this kind of model trained, yes, I think the kind of ideas here extend.
okay, so yes, thanks Jose, again. And now welcome the next speaker. So now Maria Ciudadano, Perimeter Institute, is going to talk about escaping the shadow of Bell's theory in network locality.
Hi. First, thanks for having me here. I'm Maria. I'm a PhD at Perimeter Institute, and I'm gonna talk about my latest work, supervisorily Wolf, and also with Paula Buso and Christian Pio, theorem in network quality. First, I'm gonna review some basic concepts that you may know that may sound a bit repetitive after talk. Yeah, just to have it in mind, understand the concept. So in 1964, Bell proposed his famous theorem that states if a hidden variable theory is local, it will not agree with quantum theory, and if it agrees with quantum theory, it will not be local. He proposed a thought experiment in order to prove his theorem. It consists of two parties space-like separated, named Alice and Bob, and a source that emits a state, it could be quantum. Each party, Alice and Bob, can perform measurements in their laboratories. They have isolated laboratories, and this measurement has like two choices, 0 and 1. And when you perform the measurement, you can get two different outputs, -1 and 1. This is known as the standard Bell scenario, and it has been studied a lot. You can perform the experiment many times, so you get the frequencies of A, B given X, Y, and you can get the probability distributions that are named correlations. These correlations satisfy the no-signaling principle, as you explained, which state that the output of Alice does not depend on the input of Bob, and vice versa, and is mathematically formalized by this equation. And it comes to avoid superluminal interpretations. This can be studied using the causal inference formalism, as he explained. Here, for me, the yellow circles represent observed variables, and the blue circle represent unobserved variables. And in the same way that he explained, the arrows represent the causal influence. Here, for example, X is influencing A, and Y is influencing B. And we don't have any arrow from X to B because we are satisfying the no. Then we can study, as he said, the correlations that are compatible with this DAG, the direct acyclic. Like DAG is the representation of the scenario. And the set of correlations that are compatible classically with the causal structure is called as local set and is defined by the CHSH inequalities. The CHSH inequality and its terms is the correlator, which is basically the sum of the correlations when the outputs agrees minus the sum of the correlation when the output is. This inequality is bounded by 2 when we are in classical theory. However, if we allow for quantum states and quantum theory, is bounded by 2 square root of 2. It also has an algebraic bound of 4 when we consider probability distributions that are only compatible with no signaling, and we are not imposing a quantum theory. We are considering like beyond quantum theory. Notice that the local set is strictly contained in the quantum set, and the quantum set is strictly contained in the no-signaling set. In the case of the standard Bell scenario, we have convex sets, so they are like easy to define, and the local set is defined by linear inequalities, and they are already know which are the C. However, we can generalize this concept to quantum networks. This is one of the simplest. It's called three-chain or bilocality scenario, and it consists of 3 parties connected by 2 sources in pairs. We are assuming here independence of the sources, and this makes the characterization of the set much more complex because we have a non-convex set. It's not fully defined. In the case of the bilocality scenario, which is the simplest or one of the simplest, we have computational tools in order to assess non-classicality or classicality of the correlations. But the inequalities that define the set are not defined yet. However, in more complex scenarios, we don't even have like computational tools that always give us non-classicality or classicality. And these structures, more sources, allows us to have new forms of non-classicality that are usually called genuine non. In my work, I focused on the minimal cardinality for this scenario, which is binary outputs for Alice, Bob, and Charlie, and binary inputs for Alice and Charlie. Bob has no choice, and this is the minimal cardinality that you can use to find non-classicality in this scenario. Recently, there has been many studies in the triangle network, which is the same than this network, but using another source to connect Alice and Charlie. And they are trying to get to find non-classicality with the minimum number of outputs and inputs. But there are not many studies the bilocalities. So the concept of genuine non-classicality has tried to define many times, and there are many definitions in the literature, and there are like some non-classical correlations that are claimed to be genuine, and it's a bit like difficult and controversial. For me, the genuine non-classicality is the one that cannot be traced back to the standard Bell scenario. I know that this is like a super vague definition, but I think we don't have yet the tools to perfectly define it. And with this concept, it arises some questions such as how this type of non-classicality can be tested, or if any of the non-classicality that has been claimed genuine is genuine according to our definition. In order to see what I understand as non-genuine, I'm gonna show you the examples of non-classicality in the minimal bilocal scenario. One of the most famous is the entanglement swapping scenario. Here, Bob performs a coarse-grained Bell state measurement, and Alice and Charlie are violating CHSH when Bob outputs 0. In this case, the entanglement swapping is performed when Bob outputs 0, and you can see that the correlations in this scenario are non-classical whenever Alice and Charlie are violating CHSH. So somehow you are tracing back the non-classicality to the non-classicality in the standard Bell scenario. So for me, this is non-genuine non-classicality. This example is kind of claimed as genuine in a paper where they propose a notion of non-classicality called fully network non-locality, which is the non-classicality that requires all the sources to be non-classical. But for me, come back to standard Bell scenario. Then another example is inspired by a paper by Fritz. In this case, we have a classical source between Bob and Charlie. Charlie directly outputs lambda, and lambda serves as an input for Bob. So somehow the output of Charlie becomes the input of lambda. And Alice and Bob are violating CHH. In this case also, the non-classical correlations, the correlations are non-classical whenever Alice and Bob are violating CHSH. So again, for me, this is an example of non-genuine non-classicality. So what I did was propose a definition, a new type of non-classicality that you can ensure that is genuine in the sense that I commented before. Is named minimal network non-classicality and is the one that cannot be explained with all sources being classical, but can be explained at the same time with these two DAGs. So you can explain it having one non-classical source between Alice and Bob, and one classical source between Bob and Charlie, or vice versa. In this case, I'm writing OPT because this, when you consider non-classical sources beyond quantum, you are considering operational probabilistic theories, which is basically a generalization of the notional in principle. This non-classicality is not tied to any of the sources, either originally present in the network or induced by a post-selection as in the entanglement swapping. So we can say that is kind of delocalized. And we say that this comes from the structure of the network and is theory independent because we are not restricted to quantum theory. There is no any violation of CHSH between any of the parties. That's why we can claim that you can't trace back this non-classicality to the standard Bell scenario, and it's cheap in terms of the sources in the that you only requires one non-classical source, and it can be placed anywhere in the. So my result is that I found examples of this notion of non-classicality in the simplest bilocality scenario, in the one with the minimal cardinality, which corresponds to, as I said, having binary inputs for the three parties and binary outputs for the three parties, sorry, and binary inputs for Alice and Charlie. And some of these examples are quantum, proving that this type of non-classicality is compatible with quantum theory. And this is a pictorial representation of the results that I found. This is only pictorially represented because all these sets are non-convex and are much more difficult to define. But just to understand, this is the set compatible with having only classical sources, so only local set. And this would be the set compatible with one classical source in the right and one non-classical source in the left, and this vice versa. So minimal non-locality would be this region, which is compatible with these two big sets at the same time, but is not compatible with the local set. Finally, just as a conclusion, we revisited previous notions of genuine non-classicality and argue why we think that is or not genuine. We propose also a new type of non-classicality, but I want to remark that I propose this notion as a witness of genuine non-classicality, but I'm not claiming that I'm giving a definition for genuine non-classicality. I know that this definition is not tight and we can find maybe genuine examples that are not minimal non-local, but it's a way to certify that something is genuine. We saw also the rich phenomenology in the bilocal scenario with the minimal cardinality. I think from my knowledge, there are no previous examples in this case. And as a future direction, we would like to find minimal non-local correlations in other networks. This is more difficult because in the case of the bilocality scenario, we have computational tools in order to assess the non-classicality and the compatibility with these causal structures. But when you go beyond, there are some techniques, as inflation techniques, but it's not something that works always. So we will work on that. And also, I would like to see if there is any genuine non-classical examples that are not minimal. Okay.
For your talk, are there questions? Okay, well, I'm not really familiar with this topic that you explained, but well, yeah. So how is it different from like the non-locality general, or you comment a bit?
Yeah. So this is just a type of non-locality, so it's including non-local correlations in general. It's just that usually when we are talking about quantum non-locality in networks, we are claiming that the adding an extra source is giving us like a different type of non-classicality, and we can maybe like find different protocols or different applications in that. But actually, many of the correlations that are claimed to be novel in the sense of quantum network non-locality are not novel because it's just an embedding of the standard Bell scenario. So we would like to see if there are any novelty in the quantum networks.
So thank you again. The final from now. So now we have the last speaker of the session, Pablo Parellada, and he from Universidad de Valladolid, and he's going to talk about the algebraic invariance in linear quantum optics.
Thank you very much. It's been a wonderful workshop. Thank you for having me here. So I'm going to talk a bit about our latest research, where we derive some invariant quantities that are associated with photonic quantum states, so that we have a photonic state that could be a Fock state or a coherent state. We associated a quantity that is conserved whenever we evolve that state with a linear optical interferometer. Doesn't matter which one, it is always conserved. So an immediate consequence, if we have two different states with a different value of one of the invariants, then we know it is impossible to build a linear optical interferometer that transforms one state into the other. And to do this, we are going to use some tools from Lie groups and Lie algebras and the adjoint action. So even if you are not especially interested in linear optics, these tools have been used, or similar tools have been used to study, for example, parent plateaus in variational quantum circuits. So maybe you find some ideas that are useful in other areas. Okay, so when I talk about linear optics, I'm going to talk really about passive linear optics, which is well, you can imagine it as several paths through light can travel. Could be some optical fibers, for example, and then some devices like beam splitters and phase shifters that just mix the different inputs, the different light sources in every mode. Passive linear optics doesn't include any nonlinearities, of course, and also it doesn't include parametric amplifiers or devices that change the mean number of photons. So no devices that introduce squeezing, for example. And this setup can be described classically just with a unitary matrix called the scattering matrix. So all these systems are also studied in classical optics. The simplest example is just a beam splitter, a semi-reflecting mirror that shine some light, and it is the intensity is divided. This is the basis of the Michelson-Morley interferometer that you have all seen. It's a very simple example of linear optics. We are going to study a system with more modes, but it's just um, the same spirit. So even if this system is classical, we can also treat it quantum mechanically. And what we are going to do is just evolve the creation and annihilation operators with the classical scattering matrix. We heard yesterday this can be used to study the Hong-Mandel effect, for example. And well, an immediate consequence of this formalism is that the number of photons is conserved in passive linear optics. So this is a first example of an invariant quantity that, well, everybody already knew about it, but good to. And why are we interested in linear optics? Well, some decade ago or a bit more, was proven that there is some problems, for example, boson sampling, that can be done efficiently in a linear optical interferometer, and it's very difficult to do it in a classical computer. So it gives some kind of quantum advantage. It is also very simple to work with these interferometers in the lab. You don't need cryogenic temperatures or anything. But there is a disadvantage, and that is that we cannot do full quantum computing with a linear optical interferometer. There are some unitaries that cannot be implemented deterministically. For example, you cannot do a CNOT deterministic. So yeah, not all not all unitaries can be implemented with linear optics. So we want to study what what unitaries can be actually implemented with linear optics. And to do this, we are going to give some invariants that, well, whenever we can actually implement the gates, they must be conserved. We can give a family of these invariants, and this give, as I said, a necessary condition for a state to be able to be evolved into another with. And to do this, we're going to use some tools from Lie groups and Lie algebras. As I mentioned, the classical scattering matrix that describes the linear optical system is a unitary m by m matrix, and we map its quantum version with the map of the creation and annihilation operators with this S matrix. This is a complicated map. That's why boson sampling is a difficult problem. But for to derive our invariants, we're going to work instead of the groups with the algebras. So this is the algebra of the unitary algebra of Hermitian matrices, and we're going to map it to an algebra of linear optical Hamiltonian. We get the entries of this matrix, and we map it to this Hamiltonian creation and annihilation operator. So the recipe to derive the invariants is we start with an orthonormal basis Pi of this algebra. This is important to that it is orthonormal for the next steps. Then we quantize this basis Pi. We map it this algebra homomorphism to the to a basis of linear optical Hamiltonians. So, for example, Woods, we get an orthonormal basis here. That, well, you can guess what it is. We can map it to this basis of linear optical Hamiltonian. These are the number operators and modes. But they all conserve, of course, the number of photons. So now we're going to ask the question, what is the action, the adjoint action of a linear optical unitary on this basis of linear optical Hamiltonian? We will see later why we asked this question. So, well, the adjoint action is given by this map. And using some properties of the Lie group and Lie algebra homomorphisms, we arrive to this equation. So the adjoint action is given in terms of a matrix C that, just because we chose the original basis B to be orthonormal, then this C matrix must be an orthogonal matrix. C times C transpose is the identity. And this will be the key property that we are going to use to derive the invariant. But why do we even care about the adjoint action? Well, even if you don't call it that way, the quantum evolution of a density matrix by a unitary operator is given by the adjoint action. U is a unitary and rho is a Hermitian matrix, so or operator. So it is just the adjoint action of the unitary operator on this Hermitian operator. So now, this is a very simple example of an invariant quantity in linear optics, and this had already been proposed in 2 decades ago by Soma and from Los Alamos. But the difference is that they needed this operator OI to be orthonormal. So it cannot be applied to linear optics, for example, if the number state acts on the Fock state, so it's unbounded, cannot even normalize it. So because of the trick we did with these, these B's and these O's, we don't need now this basis of linear optical Hamiltonians to be normalized. So if we evolve, prove that this is indeed invariant, we evolve the density matrix. We use the cyclic property of the trace, and now we is equivalent to evolving the elements of the basis of linear optical Hamiltonian. So we just use the property that this is given by a matrix C that is orthogonal, and because this is squared, well, it turns out that just the same quantity. So it is indeed invariant. I'm not going to show it for the sake of time, but using this same strategy, you can define more invariants. Like for example, projecting this matrix on the algebra of linear optical Hamiltonians and taking the spectrum. But let's see an example. This is the basis I gave before for linear optical Hamiltonians of two modes, and we can apply to a coherent state, for example. So we can take this as the expectation values to calculate the invariants, and turns out that this quantity must be conserved whenever we have two coherent states and evolve them with linear optics. It was already known because, well, the number of photons, but I chose this example to show that it can be applied to coherent states without any problem. And apply this to Fock states or whatever photonic states, even squeezed. So as a consequence, if two states have different invariants, well, we cannot evolve one into the other, as I said. And we can use this and other invariants to prove that, for example, we cannot prepare a Bell state from a Fock state, or a Noon state from a Fock state, or a Fock state from another Fock state if they are not permutations of one another. All this with linear optics. And as a conclusion, well, I have some necessary conditions for linear optical evolution. These invariants, for example, can be used to without impossible state preparations when trying to see what useful states we can prepare with linear optics. And these invariants have the advantage that they can be applied to states in the full Fock space, which as far as I know hadn't already been proposed. And well, some things we're working on to improve this is to try to apply this also to linear optical Hamiltonian, to active linear optical Hamiltonians, which parametric amplifiers and other useful devices. But the problem is that, well, there are some mathematical problems, so it's a bit tricky. And also try to apply this to heralded states to study probabilistic state preparation. And that's it. Thank you very much.
Thank you, Pablo. Are there questions?
Hi, thank you for the talk. I had a question that, my main question is that if you can use this Lie theory to actually propose an invariant, because, for instance, in the example that you told us about, like you took an invariant and used this property, these transformation properties under unitary to show that it's invariant, but can you actually use like the theory to propose an original invariant, or do you use only this mathematical formalism to show how these objects transform?
I'm not sure I understood the question.
I'm just trying to understand why this is not like a mathematical overkill, because the maths involved are like very hard, and I'm just trying to see where really the point is. And then my question is this Lie theory related to the actual invariant that you are proposing, or you are just like using it to show that your transform density matrix has some form to show that it is actually invariant?
Yes, mainly the point where all this Lie theory appears is with this, well, this is a Lie algebra, no, sorry, a Lie group homomorphism that maps the classical scattering matrix to the U, the quantum scattering matrix. And this is a Lie algebra homomorphism that maps the basis here, to a basis here. And well, here, for example, in these steps, we use some properties of the homomorphisms. But in the end, it's not very, you don't need like a lot of Lie theory to do this. You just need to study a bit the adjoint action.
Yeah, but that is related to actually, on how this object is transformed, right? So,
yes.
So you don't. I mean, you can't. Can you use? My question is if you can use actually Lie theory to propose invariant. I mean, because I guess that the main goal is to find interesting invariants to show that you cannot use any linear optical procedure to map one state to other. So I mean, is that? I mean, does that make sense?
Can you repeat the question?
No. Well, never mind. We can chat later.
We can talk it later.
So that's one, and then of the
With this idea, can you extract any information of the minimal element that previously disconnected?
You mean to add a nonlinear component so that any unitary can be achieved, for example?
You can add variant. Maybe you can element.
I haven't studied that, but I know there is a paper that studies what nonlinear extensions you can add. For example, if you add, I think, a Kerr nonlinearity, then you can achieve all possible unitary. So yeah, since it was more or less done, I haven't looked at it, but
Thank you, Pablo, again. So now we have lunch break, but before, let's take a picture of the group for this workshop. Just follow us. We'll do it like right now, and then we have to be back at 2:30 for the next talk.